Did gamma rays cause Earth's deadliest extinctions? Imagine a dying star whose final breath could outshine the entire history of your existence. NASA scientists tracked these cosmic time bombs, called gamma ray bursts, that release more energy in seconds than our sun generates in billions of years. In October 2022, astronomers witnessed the brightest gamma ray burst ever recorded, nicknamed the BOET, brightest of all time. Had that burst occurred in our galactic neighborhood and been pointed at Earth, our civilization might have been erased from history. So how close have we come to cosmic extinction, and could ancient GRBs, reshaping the very path of evolution, explain Earth's deadliest mass extinctions? The Ordovician extinction, Earth's first cosmic catastrophe? What if the first major mass extinction on Earth wasn't caused by volcanic activity or an asteroid, but by radiation from space? About 445 million years ago, our planet experienced the Ordovician-Silurian extinction event, the first of the big 5 mass extinctions that have punctuated Earth's history. This catastrophic event eliminated approximately 85% of marine species, fundamentally altering the course of life on our planet. The Ordovician period was a time when a majority of life existed in the oceans. There were no plants or animals on land yet, just a vast expanse of barren rock. Beneath the waves, however, life flourished in remarkable diversity. Trilobites scuttled across the seafloor alongside primitive fish, while corals, mollusks, and countless invertebrate populated the ancient seas in a thriving underwater ecosystem that seemed stable until something triggered a devastating collapse. Imagine a sudden, global catastrophe striking this vibrant marine world, like a cosmic switch being flipped, extinguishing life across the planet. What makes the Ordovician extinction particularly intriguing is its unusual pattern. The extinction unfolded in 2 distinct pulses separated by approximately 1 million years, a cosmic heartbeat that would forever alter Earth's evolutionary trajectory. During the first pulse, many species vanished rapidly across widely separated geographic regions, from what is now North America to areas that would become Europe and China. This simultaneous global impact is difficult to explain through localized phenomena. The traditional explanation for this extinction has centered on climate change triggered by continental movements. According to this theory, the ancient supercontinent Gondwana drifted over the South Pole, triggering massive glaciation that locked up ocean water in ice caps. This supposedly caused sea levels to drop dramatically, destroying shallow marine habitats where most species lived. But a closer examination reveals problems with this explanation. The fossil record shows that species disappeared too rapidly and too uniformly across different latitudes for a gradual climate shift to be the sole culprit. While climate change certainly played a role in the extinction, the trigger for this climate shift has remained mysterious. In 2004, a team of researchers from the University of Kansas proposed an alternative hypothesis that could explain these anomalies. Perhaps a gamma ray burst, GRB, from a nearby stellar explosion triggered the Ordovician extinction. This hypothesis was based on careful analysis of the fossil record and the unique signature a GRB would leave behind. Dr. Adrian Malott and his colleagues noted several features of the Ordovician extinction that aligned with their GRB hypothesis. First, the initial extinction pulse shows a pattern of rapid, simultaneous species loss across vast geographic distances, exactly what you'd expect from a global radiation event. Second, the fossil record reveals evidence consistent with radiation damage rather than just environmental change. The researchers identified fossilized malformed plant spores from the Ordovician period that show patterns of damage similar to what we see in modern plants exposed to UV radiation. While this evidence comes from later periods than the Ordovician, it establishes a precedent for identifying radiation effects in the fossil record. These malformations appear suddenly in the geological record, suggesting a rapid onset rather than gradual environmental deterioration. The double pulse pattern of the Ordovician extinction aligns with GRB impact models. The initial burst of gamma radiation would strike Earth in a flash, lasting from a few seconds to minutes, triggering the first extinction pulse through direct radiation effects and atmospheric changes. The second pulse would follow as the damaged ozone layer allowed harmful UV radiation to reach the surface, creating ongoing ecological stress that eliminated species that initially survived. To test scientific plausibility, researchers calculated the probability of Earth being struck by a gamma ray burst during its history, using data on GRB frequency observed throughout the universe, typical energy outputs, and Earth's position in the Milky Way galaxy over time. Scientists performed complex statistical analyses. Their calculations yielded a surprising result. There's approximately a 50% chance that Earth has been hit by at least one lethal gamma ray burst in the past 500 million years. Among the 5 major mass extinctions, the Ordovician event shows the strongest correlation with the expected effects of a GRB impact. If a gamma ray burst did trigger the Ordovician extinction, it would have unfolded something like this. A distant star, perhaps thousands of light years away, reached the end of its life in a spectacular supernova explosion. For a brief few seconds, this dying star focused an intense beam of gamma radiation into space. By cosmic chance, Earth happened to lie in the path of this beam. When the gamma rays reached our planet, they would have created a light show in the night sky brighter than a full moon, but most of their energy would have been invisible. The real damage would have occurred in the upper atmosphere, where the gamma rays would have triggered a cascade of chemical reactions, converting nitrogen and oxygen into nitrogen dioxide, effectively creating a brown haze of smog worldwide. This atmospheric transformation would have blocked some sunlight, causing rapid global cooling. More importantly, the nitrogen oxides would have catalytically destroyed the ozone layer, allowing harmful ultraviolet radiation from the sun to penetrate to Earth's surface and into the shallow oceans where most marine life lived. Marine organisms that had evolved in an environment protected from UV radiation would have found themselves suddenly exposed to damaging levels of ultraviolet light. DNA damage, reproductive failure, and ecosystem collapse would have followed. What makes the GRB hypothesis compelling is how it unites disparate evidence. It explains the rapid, global nature of the extinction, accounts for the double pulse pattern, and helps explain why organisms in shallow waters suffered most severely. As Thomas Johnson, a paleobiologist not involved in the original research, noted, the GRB hypothesis provides an elegant solution to several long-standing puzzles about the Ordovician extinction. His assessment highlights why many scientists now consider this cosmic explanation a serious possibility, even if absolute certainty about this ancient catastrophe remains elusive. Cosmic time bombs, the science of gamma ray bursts. Considering cosmic influences means confronting an unsettling reality. The universe regularly produces explosions that dwarf our most destructive weapons by factors beyond comprehension. These gamma ray bursts release more energy in mere seconds than our sun will produce in its entire 10 billion year lifetime. And until recently, scientists couldn't explain what natural mechanism could possibly generate such devastating power. When astronomers first detected these mysterious bursts in the 1960s, they faced a profound puzzle. What cosmic process could possibly generate such immense energy? The journey from mysterious signals to understanding these cosmic flashbulbs took decades, revealing some of the most violent events in our universe. Today, scientists classify gamma ray bursts into 2 distinct categories that unveil fundamentally different cosmic processes. Long bursts, lasting more than 2 seconds, emerge from the catastrophic deaths of massive stars. Short bursts, lasting less than 2 seconds, result from the collision of some of the densest objects in the universe. Long gamma ray bursts occur when stars at least 10 times more massive than our sun reach the end of their lives. Unlike smaller stars that might quietly fade away, these stellar giants create cosmic spectacles of extraordinary magnitude. The process begins deep inside a dying massive star. After exhausting its nuclear fuel, the star's core collapses catastrophically under its own gravity, creating a black hole in mere seconds. As this newly formed black hole devours the infalling stellar material, it forms an accretion disk. Imagine a whirlpool of superheated gas spiraling inward at tremendous speeds. This chaotic environment generates two opposing jets of particles accelerated to nearly the speed of light, blasting outward from the rotation poles like cosmic searchlights cutting through the darkness of space. Astronomers call this the collapsar model. Capturing how a stellar giant's collapse creates these extraordinary energy beams. Short bursts present an entirely different cosmic scenario. They typically result from the collision of two neutron stars, incredibly dense remnants containing the mass of our sun, compressed into a sphere roughly the size of a city. A single teaspoon of neutron star material would weigh billions of tons on Earth. When these extraordinary objects spiral into each other, they create a black hole through a process distinct from the collapsar model. The impact of these super-dense objects generates perfect conditions for cosmic alchemy, the formation of some of the heaviest elements in the universe. During these collisions, atomic nuclei rapidly accumulate neutrons to form gold, silver, platinum, and other precious metals that eventually find their way into planets like Earth. Every piece of gold jewelry you own likely originated in such a violent cosmic merger billions of years ago. In some cases, short bursts may also result from a neutron star merging with an existing black hole. The energy scale of these cosmic explosions challenges human comprehension. A typical burst releases more energy in a few seconds than our entire sun will emit during its 10 billion year existence. An output so massive that converting Earth's entire mass perfectly into energy would still fall short of the most powerful bursts observed. These bursts aren't omnidirectional, but produce focused beams that slice through the cosmos like celestial spotlights. This directionality explains why we detect only a fraction of all gamma-ray bursts. We only see those where the beam points toward Earth. The focused nature also explains their destructive potential. When a burst points directly at a planet, it concentrates its energy rather than dispersing it equally, potentially affecting worlds that lie in its path. Scientists estimate gamma-ray bursts occur approximately once per day across the observable universe, mostly in distant galaxies billions of light years away. Their tremendous brightness allows detection even at these extreme distances, making them valuable cosmic beacons for understanding the early universe. The detection of these events represents a triumph of modern astronomy. Gamma rays don't penetrate Earth's atmosphere, so their discovery awaited the space age when detectors could be placed above our protective shield. The first bursts were actually discovered accidentally by satellites monitoring nuclear test ban treaties in the 1960s. Scientists initially considered possibilities like alien civilizations or secret nuclear tests before discovering the truth. Gamma-ray bursts represent the most energetic electromagnetic events since the Big Bang itself. Supernovae, solar flares, even active galactic phases, none compare to the raw power of a gamma-ray burst at its peak. This enormous energy output creates an intriguing possibility. These bursts might be visible across much of the observable universe. Some scientists suggest advanced civilizations might harness artificial gamma-ray bursts as beacons to announce their presence across intergalactic distances. But for life-bearing planets, these cosmic lighthouses represent potential extinction events. Their energy can strip away protective atmospheric layers and bathe planetary surfaces in lethal radiation, especially if a burst occurs relatively nearby, with its beam pointing directly at an unfortunate world. Research continues to yield new insights. Recent observations have identified ultra-long bursts lasting hours instead of seconds, suggesting additional creation mechanisms we don't yet understand. Others have shown evidence of gravitational waves accompanying short bursts, confirming their origin in neutron star mergers and opening new avenues for multi-messenger astronomy. Atmospheric assault: how gamma rays attack Earth's shield. What stands between us and the harsh radiation of space? A fragile layer of ozone, just a few millimeters thick if compressed to sea level pressure. When a gamma ray burst strikes this delicate shield, it triggers a cascade of atmospheric chemistry that transforms our protection into vulnerability. Unlike many cosmic threats that directly impact Earth's surface, gamma ray bursts wage their assault through more subtle means. The gamma rays themselves don't penetrate to ground level. Instead, they unleash their destructive potential by fundamentally altering our atmosphere's protective chemistry. This invisible attack makes GRBs particularly insidious, as their most devastating effects unfold through a series of atmospheric chain reactions. The ozone layer, our thin atmospheric armor, absorbs the majority of the sun's harmful ultraviolet radiation before it can reach the surface. This slender shield of triatomic oxygen molecules protects all terrestrial life from DNA-damaging radiation. Without it, life as we know it couldn't exist on land. But this protective veil becomes surprisingly vulnerable when confronted with a gamma ray assault. When gamma rays penetrate our upper atmosphere, they immediately ionize atmospheric gases, splitting apart nitrogen and oxygen molecules. This splitting creates nitrogen oxides that act as catalysts, systematically dismantling our ozone shield molecule by molecule. Each nitrogen oxide can destroy thousands of ozone molecules before being removed from the atmosphere, a devastatingly efficient process. The scale of potential destruction is sobering. Models indicate that a mere 10-second exposure to a nearby gamma ray burst could deplete up to 75% of the ozone layer in regions directly exposed to the radiation. Global ozone levels could drop by as much as 38%, creating a worldwide crisis far exceeding any atmospheric damage humans have ever caused or witnessed. This depletion wouldn't manifest as a uniform thinning. Instead, it would create dangerous holes in our protective shield, similar in concept to the Antarctic ozone hole from chlorofluorocarbons, but potentially far more extensive. Through these atmospheric wounds, harmful ultraviolet radiation would flood onto Earth's surface at levels life hasn't experienced since before the ozone layer formed. The geographic distribution adds another layer of complexity. When gamma radiation enters the atmosphere over a polar region, the depletion becomes concentrated there rather than spreading uniformly. This occurs because the radiation produces chemical changes primarily in the middle atmosphere, and atmospheric transport flows predominantly toward the pole. Consequently, polar regions could experience even more extreme ozone destruction than global averages suggest. Our atmosphere wouldn't remain compromised permanently. Models suggest the ozone layer would gradually recover over approximately 5 to 7 years. During this recovery, ozone in the lower atmosphere might measure around just 10 parts per billion, varying seasonally. Imagine stepping outside into a sun that burns without mercy day after day for years. A world where shadows become sanctuaries and exposed skin blisters within minutes. The severity depends largely on the fluence of the burst, essentially the total energy delivered per unit area. A more energetic burst, or one directed more precisely at Earth, would cause greater atmospheric disruption. Local ozone depletion in the worst affected regions could reach 74%, creating areas where almost no protection remains against the sun's ultraviolet radiation. Visualize our atmosphere as a complex chemical factory with carefully balanced production lines. Gamma rays sabotage key workstations, causing harmful compounds to form while shutting down protective processes. The factory doesn't explode. It begins manufacturing the very chemicals that slowly dismantle its protective systems. This atmospheric damage represents a fundamental difference from other extinction-level threats. An asteroid impact or supervolcano eruption would affect our atmosphere primarily through dust and debris that eventually settle. The chemical changes triggered by gamma ray burst would be more persistent, altering atmospheric chemistry for years after the burst has passed. The atmospheric ozone we rely on daily exists through a delicate balance of formation and destruction. Oxygen molecules split by ultraviolet radiation from the sun allow individual oxygen atoms to combine with other oxygen molecules to form ozone. The gamma ray burst shifts this equilibrium by introducing new destruction pathways that overwhelm the natural formation processes. Our modern understanding comes from sophisticated atmospheric models combining astrophysics with atmospheric chemistry. These reveal that even a relatively distant GRB could trigger significant ozone depletion if Earth happens to be in the path of its narrow beam of radiation. Perhaps most concerning is how quickly this transformation would occur. Unlike climate change or other gradual atmospheric alterations, the chemical reactions initiated by a gamma-ray burst would begin immediately and accelerate rapidly. Within days, significant ozone depletion would already be underway. Ecosystems would have little time to adapt as the sky itself becomes a threat. This atmospheric assault would ultimately transform Earth's surface environment through the flood of solar ultraviolet radiation penetrating the compromised ozone layer. UVB radiation, causing sunburns and DNA damage, would increase dramatically. The more energetic UVC radiation, normally completely blocked by our atmosphere, might reach the surface in measurable amounts for the first time in Earth's recent history, bathing the planet in radiation hostile to the very foundation of life. Extinction Cascade, life under deadly skies. As deadly UV radiation floods through the atmospheric wounds, a silent extinction would begin unfolding across Earth's surface. The organisms we rely on most would face the greatest peril. This isn't just about individual species struggling. It's about the collapse of the fundamental biological systems that maintain life as we know it. In the oceans, microscopic phytoplankton would become the first major casualties. These tiny organisms form the foundation of the entire marine food web and generate approximately half of our planet's oxygen supply through photosynthesis. Their cellular structures, evolved in an environment historically shielded from extreme UV exposure, possess minimal natural defenses against radiation. Diatoms and coccolithophores, two common phytoplankton types crucial for carbon cycling, would suffer severe DNA damage when bombarded by UVB and the normally blocked UVC radiation, disrupting their delicate molecular machinery. Within days, the damage would be evident across entire phytoplankton populations as their photosynthetic efficiency plummets. Research on Antarctic phytoplankton has demonstrated that even moderate increases in UV exposure can reduce their growth rates by 30%. And a post-gamma ray burst scenario would subject them to radiation levels far beyond anything in our recent planetary history. The effects would rapidly travel upward through the marine food chain. Zooplankton would starve as their food source disappears. Fish populations would subsequently crash, affecting species that rely directly on plankton, then extending to larger predatory fish. The entire marine ecosystem would begin unraveling from its foundation. On land, terrestrial plants would experience an immediate assault on their photosynthetic capabilities. The intense UV radiation would degrade chlorophyll molecules, essentially disabling plants' ability to convert sunlight into energy. Cellular damage would accumulate rapidly, with radiation directly attacking plant DNA. Particularly vulnerable would be staple crops like wheat and rice, whose shallow root systems and exposed growth patterns leave them with little natural protection. Plant reproduction would suffer dramatically. Pollen viability would decrease, and the delicate tissues of flowers and developing seeds would experience disproportionate damage. Within seasons, widespread plant communities would transform radically, with certain species vanishing entirely while others maintain reduced populations. Surface-dwelling animals would face devastating challenges. Unlike microorganisms with rapid reproduction cycles that can quickly adapt through natural selection, larger animals with longer generation times would have no opportunity for evolutionary adaptation. Their exposed tissues, particularly eyes and skin, would suffer immediate and cumulative damage. Animals would develop severe radiation burns, weakening their overall health and making them vulnerable to infections. Vision impairment and blindness would become widespread as sensitive ocular tissues absorb harmful radiation, hampering hunting, foraging, and predator avoidance. Immune systems would gradually collapse as UV radiation damages white blood cells. Amphibians, already experiencing global declines, would be particularly vulnerable as their permeable skin offers minimal protection against radiation. Natural adaptations would determine survival chances. Animals with pigmentation like melanin would gain some protection. Those with thick fur, feathers, scales, or shells would fare better than animals with exposed skin. Nocturnal species would have a significant advantage over diurnal ones, venturing out only when the sun's radiation is absent. Geographic position would play a crucial role in determining fate. The poles would likely experience the most severe ozone depletion, making polar ecosystems particularly vulnerable despite their limited sun exposure. Equatorial regions might retain more ozone protection, but would still experience dramatically increased UV exposure. 3 groups stand out as potential survivors. Deep-sea organisms would remain largely insulated from the catastrophe. Water effectively absorbs UV radiation, with significant attenuation occurring in just the first few meters. Creatures living hundreds or thousands of meters below the surface would continue their lives largely unaffected, protected by the water column above them. Burrowing animals that spend most time underground would find unexpected sanctuary. The soil would block virtually all harmful radiation, allowing these species to continue their subterranean lives while surface dwellers perish. This includes earthworms, burrowing insects, and mammals like moles and prairie dogs, which might emerge occasionally for food, but quickly retreat to safety. Extremophiles, organisms already adapted to extreme conditions, form a third group with superior survival potential. Many have evolved sophisticated DNA repair mechanisms that allow them to withstand normally lethal radiation levels. Tardigrades stand out for their remarkable radiation resistance, surviving doses thousands of times higher than would kill humans. Survival mechanisms reveal a fascinating biological arsenal against radiation that has evolved over billions of years. Some organisms produce radiation-absorbing pigments. Others maintain enhanced DNA repair systems that quickly fix radiation-induced damage. Certain species have biochemical adaptations, preventing the formation of damaging free radicals. A few exceptional organisms can enter suspended animation when conditions become lethal. Behavioral adaptations would become crucial survival strategies. Many animals would likely shift toward nocturnal activity patterns, emerging only after sunset. Others might migrate to areas with greater natural protection, seeking densely forested regions where canopy coverage provides shielding or higher elevations where thicker air offers marginally better filtration. The ecological transformation would create a sorting event unlike any in human history, dividing Earth's organisms into those with pre-existing radiation defenses and those without. This highly selective process would favor specific adaptations, resulting in radically simplified ecosystems dominated by radiation-resistant species. A planet, the End-Permian mystery. Did cosmic rays cause Earth's worst die-off? History suggests that mass extinctions favor organisms with specific adaptations, but the most devastating die-off our planet ever experienced contains an astronomical mystery. What if the Great Dying that wiped out nearly all life 252 million years ago wasn't triggered by forces on Earth, but by a cosmic catastrophe that left its fingerprints in ancient fossils? The End-Permian extinction stands as Earth's most catastrophic biological crisis. This event eliminated over 90% of marine species and approximately 70% of terrestrial vertebrates in a geological instant. For decades, scientists have attributed this mass extinction to massive volcanic eruptions from the Siberian traps, which pumped greenhouse gases into the atmosphere, triggering extreme climate change. However, this explanation comes with persistent puzzles that haven't been fully resolved. When researchers examine the End-Permian fossil record closely, they find extinction patterns that don't align perfectly with what we'd expect from volcanic activity alone. The traditional volcanic hypothesis struggles to account for the remarkable speed of the extinction and its highly selective nature. Some organisms vanished almost instantly across widely separated regions, while others with seemingly similar environmental requirements managed to survive. This selectivity hints at an additional mechanism at work, one that might have come from beyond our atmosphere. The fossil evidence contains unusual smoking guns pointing toward radiation damage. Plant spores from End-Permian sediments reveal widespread malformations across multiple continents. These deformities include fused pollen grains and abnormalities consistent with genetic damage from high-energy radiation. The global distribution pattern suggests a planet-wide radiation event rather than localized environmental stress. These malformed plant spores bear striking similarities to radiation damage observed in modern plants exposed to high levels of radiation. The specific types of fusion and developmental abnormalities match what we see in controlled laboratory settings where plants are deliberately exposed to radiation. Another critical piece of evidence comes from atmospheric signatures preserved in End-Permian rocks. Geological records indicate a sudden collapse of the ozone layer coinciding precisely with the extinction boundary. This atmospheric disruption would have exposed Earth's surface to dangerous levels of ultraviolet radiation, an effect that overlaps with what models predict would happen following a gamma-ray burst. The formation of specific nitrogen compounds found in these boundary layers aligns with the chemical reactions that would occur if gamma rays interacted with Earth's upper atmosphere. Research teams from the University of Kansas and NASA have proposed that these anomalies could be better explained by gamma-ray burst than by volcanic activity alone. Their models demonstrate how a relatively brief but intense GRB could have triggered the specific atmospheric changes observed in the geological record. According to their calculations, a gamma-ray burst lasting mere seconds could have initiated a cascade of chemical reactions in the atmosphere, depleting the ozone layer and allowing deadly UV radiation to penetrate to the surface. The researchers found that a GRB would have been particularly devastating to the ecosystems of the Permian period. The majority of life during this time was aquatic or lived near water surfaces, precisely the environments most vulnerable to increased UV radiation. Their atmospheric simulations show that the specific pattern of ozone depletion following a GRB would create extinction patterns consistent with what we observe in the End-Permian fossil record. Marine ecosystems, which suffered the most severe losses during the End-Permian extinction, would have been especially affected by the radiation aftermath of a GRB. Surface-dwelling marine organisms would have experienced direct DNA damage from increased UV radiation. This explains why certain groups like trilobites, which had dominated marine ecosystems for hundreds of millions of years, disappeared completely, while some deep-water organisms managed to survive. The terrestrial fossil record reveals that land animals with specific adaptations, burrowing behaviors, nocturnal lifestyles, or effective melanin production show higher survival rates than their counterparts lacking these traits. These adaptations would provide protection against increased surface radiation following ozone depletion, adding further weight to the cosmic radiation hypothesis. Geochemical evidence provides additional support for the GRB theory. Researchers have identified unique chemical signatures in End-Permian boundary layers that indicate sudden, intense radiation events. These signatures include isotopic anomalies and radiation-induced mineral alterations that are difficult to explain through volcanic processes alone. When mapped globally, these chemical markers show a pattern consistent with a planet-wide radiation event, a cosmic fingerprint left behind in ancient rocks. Scientists calculate the probability of a gamma-ray burst triggering the End-Permian extinction by combining astronomical data with Earth's geological record. They analyze the frequency of GRBs throughout the Milky Way, model Earth's position within the galaxy over geological time, and calculate the danger zone around potential GRB sources. This analysis determines how often Earth would have passed through these zones during its 4.5 billion year history. By factoring in the directional nature of GRBs, which emit energy in narrow beams rather than in all directions, scientists can estimate the probability of Earth being in the wrong place at the wrong time. The position of our solar system within the Milky Way influences our GRB risk. Earth's orbit takes us through different regions of the galaxy over hundreds of millions of years, sometimes bringing us closer to areas with higher concentrations of massive stars. Tracking these orbital cycles helps scientists identify periods when Earth would have faced elevated GRB exposure. When all these factors are combined, researchers can calculate probabilistic risk models. These models suggest that Earth has likely experienced at least one significant GRB impact during its biological history, with the End-Permian extinction representing a potential candidate based on the unique evidence preserved in its fossil record. The GRB hypothesis doesn't necessarily replace the volcanic explanation entirely. Many scientists now consider the possibility that the End-Permian extinction resulted from multiple coinciding catastrophes. A perfect storm scenario where volcanic activity and a cosmic radiation event combined to create particularly devastating conditions for life on Earth. The BOAT, when the brightest explosion ever lit up our instruments. While scientists theorize about cosmic events from millions of years ago, astronomers witnessed something extraordinary just 2 years ago. On October 9th, 2022, our detection instruments captured a gamma ray burst so intense it saturated sophisticated space telescopes and revealed unprecedented physics at work. This extraordinary stellar explosion became the most powerful gamma ray event ever recorded. The cosmic spectacle, officially designated GRB 221009A, quickly earned the nickname BOAT, the brightest of all time. What makes this particular burst remarkable is its intensity and the wealth of data it provided during its brief appearance. Astronomers across the globe had front row seats to an event that might occur only once every 10 millennia. A cosmic tidal wave washing over our instruments with unimaginable force. The gamma ray burst announced itself by temporarily overwhelming virtually every space-based gamma ray instrument in orbit. NASA's Fermi Gamma Ray Space Telescope found its detectors completely saturated by the incoming radiation. The burst power was so immense that even amateur astronomers with modest equipment detected its aftermath, a rare occurrence for these typically specialized observations. To comprehend the magnitude of what astronomers witnessed, consider the raw energy involved. GRB 221009A registered approximately 70 times brighter than any previously documented gamma ray burst. During its brief 5-minute appearance, lasting just 290 seconds, this single stellar explosion released roughly 1,000 times more energy than our sun will generate throughout its entire 4.5 billion year lifetime. For that fleeting moment, this solitary dying star outshone the combined light output of all the hundreds of billions of stars in our entire Milky Way galaxy. The James Webb Space Telescope turned its mirrors toward the event's location to study both its afterglow and any potential supernova association. This observation presented unique challenges since the burst happened to lie behind a thick layer of cosmic dust within our own Milky Way galaxy. Webb's mid-infrared capabilities allowed astronomers to peer through this dust barrier with unprecedented clarity. Despite the observatory's advanced capabilities, the Webb telescope's observations yielded a surprising result. Scientists couldn't find definitive evidence of a bright supernova associated with the burst. This unexpected finding has prompted astronomers to reconsider existing models of how these massive explosions unfold. The most scientifically significant discovery came when researchers detected gamma-ray spectral lines reaching energies up to 37 million electron volts, MeV, the highest energy spectral line features ever observed from any celestial object. These emission lines behaved in a revelatory pattern. The line energy varied as a power law function of time, while the ratio of line width to line energy remained almost constant throughout the observation period. This consistency provided convincing evidence that these spectacular emission lines originated from the gamma ray burst itself, rather than from any background source. The research team proposed that these emissions likely resulted from the annihilation of electrons and their antimatter counterparts, positrons, within the burst's high-energy jet. For this interpretation to be correct, the annihilating particles must have been moving toward Earth at approximately 99.9% the speed of light to produce an emission line peaking at 12 MeV. This observation provides a rare opportunity to study matter-antimatter interactions in one of the universe's most extreme environments. The BOET discovery serves as a cosmic laboratory, allowing researchers to test theoretical models against actual observations of an extreme case. When phenomena reach such intensity, they often reveal physical processes that remain hidden in more typical examples, similar to how engineers learn more from stress testing materials to failure than from routine operation. The unprecedented gamma-ray emission lines have already prompted scientists to refine their understanding of the physical mechanisms powering gamma-ray bursts. The observations support models suggesting these bursts create highly relativistic jets, streams of particles moving at nearly light speed, and that intense magnetic fields play crucial roles in focusing and accelerating material during these cataclysmic events. Equally significant is what the James Webb observations didn't find: the absence of clear evidence for certain heavy elements, including platinum and gold, deepens the ongoing mystery surrounding their cosmic origins. Many astronomers had theorized that gamma-ray bursts might be primary factories for creating such heavy elements. The BOET observations suggest the picture may be more complicated. The event demonstrated the remarkable capabilities of our current observational network. Despite being completely overwhelmed by the burst intensity, our detection systems performed precisely as designed, capturing data while automatically alerting astronomers worldwide to turn additional instruments toward the event. This coordinated response allowed scientists to observe the burst across multiple wavelengths simultaneously. For the cosmic perspective, this recent burst serves as a vivid reminder of the extraordinary energies routinely unleashed throughout our universe. If such an event had occurred within our own galaxy and been aimed directly at Earth, the consequences could have been profound, potentially creating an extinction-level event similar to those hypothesized in Earth's distant past. Fortunately, GRB 221009A originated in a galaxy approximately 2.4 billion light-years away, far too distant to pose any danger to Earth. Its energy had dissipated across the vast cosmic distances before reaching our planet, providing the perfect scenario for scientific observation. The detection of the BOET gamma-ray burst provides a crucial data point in our understanding of these cosmic phenomena and their potential role in Earth's biological history. By studying such extreme events in distant galaxies, scientists gain insights into similar occurrences that may have influenced life's development on our planet over billions of years. This extraordinary observation highlights how much remains unknown about gamma-ray bursts despite decades of study. Each new observation, particularly one as exceptional as GRB 221009A, reveals unexpected features and challenges existing models as researchers analyze the wealth of data collected during those brief but extraordinarily informative minutes in October 2022. Cosmic Signals: how we monitor the deadliest force in the universe. Beyond scientific discovery lies a more urgent question. If a gamma-ray burst were aimed directly at Earth, would we see it coming? The answer depends on an intricate global detection system that functions as our early warning network against these cosmic threats. While we can't predict when a star will collapse, we can detect the resulting explosion almost instantly when it happens. Monitoring the most energetic explosions in the universe presents unique challenges. Gamma-ray bursts appear without warning from random directions across the cosmos. Their fleeting nature, lasting from milliseconds to minutes, means astronomers have only brief windows to gather critical data. The vast distances involved further complicate detection, with many bursts originating billions of light-years away, their signals weakened by their journey across space. The Neil Gorell Swift Observatory has transformed our understanding since its launch in November 2004 as part of NASA's Medium Explorer program. This space-based observatory was specifically designed to tackle the GRB detection challenge. Swift earned its name from its ability to rapidly swivel to face newly detected bursts within seconds. Could this agility be our most crucial defense against cosmic catastrophe? Swift's effectiveness comes from its integrated instrument system. The observatory scans about 1/6 of the entire sky at any moment for the initial gamma-ray flash. When it detects a burst, Swift immediately pivots toward the source, bringing its other instruments into play to capture the burst's afterglow across multiple wavelengths. This comprehensive approach provides astronomers with a complete picture of each event. Swift's response time proves particularly impressive. Within seconds of detecting a burst, the observatory calculates its position with remarkable precision. This location data is immediately relayed to ground stations, where automated systems distribute the coordinates to observatories worldwide. What if this rapid notification system is our only chance to understand these cosmic explosions before their evidence fades away? The 2022 BOET event demonstrated this alert system's effectiveness. Within minutes of detection, observatories across multiple continents redirected their instruments to study the burst's afterglow. This coordinated response captured unprecedented data about this record-breaking cosmic explosion, showcasing how the modern GRB detection network functions as a unified global system rather than isolated facilities. At the heart of this international collaboration is the Gamma Ray Burst Coordinates Network, GCN. This system distributes alerts and preliminary data to participating observatories within seconds. When Swift detects a significant burst, the GCN triggers a cascade of automated responses worldwide. Telescopes operating across different wavelengths focus on the event, with each instrument capturing different aspects of the burst's physics. These observations are critically time-sensitive. A burst's afterglow begins fading immediately after the initial explosion, with the brightest features often disappearing within minutes or hours. Each passing minute degrades the quality of data astronomers can collect. Swift's ability to provide precise coordinates within 20 to 75 seconds of detection often makes the difference between capturing valuable data and missing the event entirely. Once observatories capture this flood of data, astronomers begin analyzing it. They determine the burst's distance by measuring its redshift, how much the expansion of the universe has stretched its light. This calculation reveals not only how far away the burst occurred, but also how long ago, since distance and time intertwine at cosmic scales. For distant bursts, we're observing explosions that happened billions of years in the past. By measuring a burst's brightness across different wavelengths, astronomers can discern whether it resulted from a collapsing star or merging neutron stars. The afterglow reveals detailed information about the original explosion's environment and the mechanisms driving the burst. From a planetary protection perspective, astronomers assess each burst's potential threat level to build models of what would happen if a similar burst occurred within our cosmic neighborhood. These assessments consider factors like energy, duration, and beam orientation relative to Earth. Today's near-instantaneous response capability has transformed GRB astronomy from a field of missed opportunities to one of the most dynamic areas in astrophysics. Before Swift's launch, pinpointing a burst location often took hours or days, long after its most informative features had faded. Despite these remarkable capabilities, our detection systems have significant limitations. We can only observe bursts after they've happened, never predict them in advance. What would happen if we could forecast these events? The directional nature of gamma-ray bursts means we only detect those pointed toward Earth, leaving us blind to bursts aimed elsewhere. And while our instruments grow more sensitive, extremely distant or faint bursts may still escape detection. If a nearby star were to produce a gamma-ray burst aimed at our planet, we would have no advance warning. The initial gamma rays would reach Earth at light speed, simultaneously with our first detection. Any protective measures would necessarily be reactive rather than preventive. This sobering reality drives astronomers to identify potential GRB progenitor stars in our galactic neighborhood, stars massive enough to potentially produce a burst. The search for these cosmic time bombs involves cataloging massive stars within our galaxy, particularly Wolf-Rayet stars, extremely hot, luminous stars shedding their outer layers rapidly. By monitoring these stars for instability signs, astronomers hope to identify potential threats, even though predicting exactly when they might produce a gamma-ray burst remains beyond our capabilities. Our global network of cosmic sentinels continues to evolve with new observatories, enhancing our detection capabilities each decade. The James Webb Space Telescope has already demonstrated its value in studying burst afterglows with unprecedented detail, potentially shortening response times and increasing sensitivity to distant events. Galactic danger zones. Could nearby stars threaten Earth? As astronomical instruments peer into the depths of space, tracking distant gamma-ray bursts, what potential cosmic time bombs might be hiding in our own celestial backyard? The most massive stars in our galaxy, those with more than 30 times the Sun's mass, harbor the potential to transform from magnificent stellar beacons into engines of destruction under very specific conditions. A star must possess an extraordinary combination of traits to become a GRB progenitor. Exceptional mass exceeding 30 solar masses, low levels of heavy elements, what astronomers call low metallicity, and rapid rotation. This rare confluence creates the precise conditions where a dying star can unleash the focused energy beams that define gamma-ray bursts. When such a massive star exhausts its nuclear fuel, its core collapses catastrophically. This implosion can form a rapidly spinning black hole surrounded by a whirling disk of infalling matter. The intense gravitational forces and magnetic fields channel this material into oppositely directed jets that blast outward at nearly the speed of light, boring through the star's outer layers. These jets, narrow, focused beams of particles and energy, are what we detect as gamma-ray bursts from Earth. Several stellar systems in our galactic neighborhood fit this concerning profile. Perhaps the most notorious is Eta Carinae, a volatile stellar system approximately 7,500 light-years from Earth. This massive binary has demonstrated its instability through dramatic eruptions throughout its observable history. During one such outburst in the 1840s, it briefly became the second brightest star in our night sky, despite its considerable distance. Today, Eta Carinae remains one of astronomy's most monitored objects precisely because of its explosive potential. Another candidate worthy of attention sits about 8,000 light-years away, WR-104, a prime example of a Wolf-Rayet star. These rare stellar objects are essentially massive stars caught in the act of shedding their outer hydrogen layers at tremendous rates, revealing the helium-burning cores beneath. What makes WR-104 particularly interesting and potentially concerning is that it exists in a binary system with another massive star, creating conditions that could enhance its explosive potential. The galactic center represents another region of interest. The heart of our Milky Way contains a dense population of massive stars, including many that meet the criteria for potential GRB progenitors. However, their greater distance, roughly 26,000 light-years, provides an additional buffer of safety compared to closer candidates. When assessing the actual threat posed by these stellar neighbors, astronomers consider multiple factors. Distance matters tremendously. The energy from a gamma-ray burst dissipates with the square of the distance, meaning a burst from twice as far away carries only 1/4 the energy. The orientation of the star's rotation axis represents perhaps the most crucial factor. Since gamma-ray bursts emit their energy in narrow beams rather than spherically in all directions, the star's axis must be pointed almost directly at Earth for us to experience the full impact. This directional nature of gamma-ray bursts works like cosmic laser pointers, incredibly powerful but incredibly precise in their targeting. This characteristic is both concerning and reassuring. The focused nature of the beams means the energy isn't spread thinly across space, but concentrated into deadly jets. However, this same property makes it statistically unlikely that any particular burst would be aimed directly at our solar system. Most of the explosion energy from gamma-ray bursts is collimated into narrow jets, meaning the vast majority of such explosions throughout our galaxy would miss Earth entirely. Astronomers meticulously analyze the rotation and orientation of potential GRB candidates. Take WR-104. Initial observations suggested its rotation axis might be uncomfortably aligned with our line of sight. However, more recent analyses have indicated the alignment isn't as precise as initially feared. The star's axis appears to be tilted at an angle that would likely direct any future gamma ray burst away from Earth's position. The massive star model doesn't explain all types of gamma ray bursts, particularly the short-duration variety. Strong evidence indicates that some short gamma ray bursts occur in environments with no star formation and no massive stars, such as elliptical galaxies and galaxy halos. These bursts likely result from the merger of compact objects like neutron stars rather than from massive star collapses. When calculating the odds of Earth experiencing a dangerously close and properly aligned gamma-ray burst, astronomers consider the frequency of these events, the distribution of potential progenitor stars, and the narrow beaming angle of the emissions. The resulting probability is incredibly remote, about one direct hit every 100 million to billion years. Put simply, you're far more likely to win multiple consecutive lottery jackpots than witness Earth in the crosshairs of a gamma-ray burst. This statistically reassuring assessment doesn't mean we should ignore these cosmic neighbors. The potentially catastrophic consequences warrant continued monitoring. The energy released in a typical gamma-ray burst exceeds what our sun will generate in its entire 10 billion year lifespan, concentrated into mere seconds. If precisely aimed at Earth, this energy would initiate the atmospheric cascade of destruction we've explored previously. Our understanding of gamma-ray burst physics continues to evolve. The conditions necessary for producing a GRB are even more specific than initially thought. Many massive stars that appear to be candidates might lack some crucial characteristic. Perhaps their metallicity is too high or their rotation rate insufficient. What would happen if astronomers discovered a nearby star on the verge of producing a gamma-ray burst aimed directly at Earth? Unlike with asteroids or comets, we would have no defensive options. The gamma rays would travel at light speed, meaning we would only know about the burst as it arrived. This sobering reality highlights our cosmic vulnerability, a reminder that despite our technological achievements, we remain cosmic perspective, living in a universe of extremes. The powerlessness we would face against an incoming gamma-ray burst mirrors our ancestors' position throughout Earth's history, unwitting participants in a cosmic lottery that occasionally deals catastrophic hands. Yet paradoxically, these same devastating events may have created the evolutionary opportunities that eventually led to human consciousness itself. For centuries, we viewed Earth's biological narrative through a purely terrestrial lens. When scientists discovered evidence of mass extinctions in the fossil record, they naturally sought explanations rooted in earthly mechanisms: volcanic eruptions, asteroid impacts, climate shifts, or continental drift. This perspective made sense. After all, these were forces we could observe, study, and sometimes even predict. But as our astronomical tools have grown more sophisticated and our understanding of cosmic phenomena has deepened, a profound shift has occurred in how we interpret our planet's biological history. The recognition that gamma-ray bursts could potentially trigger extinction events has fundamentally altered this terrestrial-focused paradigm. Earth's evolutionary story is inseparable from the cosmos. Events originating billions of light years away might have repeatedly and dramatically reshaped life on our planet, creating what biologists call evolutionary bottlenecks, moments when only a small fraction of species survive to repopulate the world, like rare survivors washing ashore after a cosmic tsunami. This cosmic perspective transforms how we conceptualize the tree of life. Evolution emerges as a complex dance between terrestrial forces and cosmic influences that periodically prunes entire branches of the evolutionary tree while creating opportunities for others to flourish. The mammals that eventually gave rise to humans might never have diversified had cosmic radiation not contributed to the dinosaurs' demise, making our very existence the product of a cosmic roll of the dice. The implications extend far beyond Earth. As we search for life on distant worlds, the possibility of gamma-ray burst extinctions forces us to reconsider what makes a planet truly habitable. Identifying worlds with suitable temperatures and liquid water is insufficient. We must also assess their cosmic neighborhood and history. A planet might appear perfect for life in all traditional aspects, yet remain lifeless if it resides too close to potential GRB sources or has recently experienced such an event. Astrobiologists factor this reality into their search strategies. When evaluating potential habitable zones around stars, they consider the temperature range alongside the star's position within its galaxy. Planets orbiting stars near the galactic center, with its higher concentration of massive stars and greater GRB frequency, might face sterilization too often for complex life to evolve despite otherwise perfect conditions. Planets in certain parts of globular clusters might experience frequent cosmic reset buttons that repeatedly wipe out emerging biospheres. Our understanding of Earth's atmosphere has been revolutionized by studying potential GRB impacts. The recognition that gamma rays could trigger a cascade of chemical reactions depleting our ozone layer has led to deeper insights into atmospheric chemistry and the delicate balance that protects surface life. Scientists now have a more nuanced understanding of how nitrogen oxides form in the upper atmosphere and their role in catalytically destroying ozone molecules. Knowledge valuable for modeling cosmic catastrophes and understanding human-caused climate change. This research has highlighted the ozone layer's crucial protective function, a thin blue shield in our planet's grand armor. By modeling extreme scenarios where this shield is compromised by cosmic radiation, scientists gain insight into concerning scenarios involving atmospheric damage from other sources. The ozone layer has likely been compromised and subsequently recovered multiple times throughout our planet's long history, each time rewriting the possibilities for life below. Perhaps most profound are the philosophical implications of living in a universe where random cosmic events can reset evolution's clock. Throughout human history, we've sought patterns and purpose in natural events, creating narratives that place our species at the center of a meaningful cosmic story. The realization that Earth's biological history might be punctuated by random, unpredictable events originating far beyond our influence challenges these comforting narratives. If gamma-ray bursts have indeed shaped Earth's evolutionary trajectory, then chance plays a far greater role in our existence than many philosophical and religious traditions have acknowledged. The dinosaurs didn't fail. They simply had the cosmic misfortune to exist during a period when Earth's protective shields were compromised. Mammals were beneficiaries of a cosmic lottery, finding themselves with empty ecological niches awaiting their expansion. Human consciousness, the very awareness that allows us to contemplate these cosmic threats, might itself be the indirect product of past catastrophic events. Our capacity to detect and study gamma-ray bursts is both ironic and profound. The consciousness potentially resulting from past cosmic catastrophes now strives to understand those very events. We are like readers who have discovered we're characters in the story, turning pages in a universal saga written partly in the violent language of gamma rays. As we look toward humanity's future, this cosmic perspective offers both humility and hope. The humility comes from recognizing our vulnerability to forces beyond our control. Despite all our technological achievements, we remain subject to cosmic processes that operate on scales we can barely comprehend. Yet hope emerges from a realization that life on Earth has survived multiple potential extinction events, each time rebounding with new forms and adaptations. For scientists studying Earth's biological history, this integrated perspective resolves long-standing puzzles. Extinction events that seem too rapid or widespread to be explained by terrestrial causes alone make sense when cosmic triggers are considered. Patterns in the fossil record become comprehensible when viewed through this cosmic lens. Pages in Earth's biography where the ink was supplied by distant stars. Future risks, the next billion years. Looking beyond Earth's past extinction events raises a more urgent question. What are our cosmic prospects for the future? Astronomical models provide intriguing insights into the statistical likelihood of Earth encountering another gamma-ray burst in the coming eons. The mathematics of cosmic threat assessment involves complex variables. The distribution of potential GRB sources throughout the Milky Way, their frequency of occurrence, and perhaps most importantly, Earth's changing position within our galaxy. Understanding these factors is fundamental to assessing our planet's long-term habitability. Earth's cosmic address plays a crucial role in determining our exposure to these energetic events. Our position within the Milky Way is constantly changing as the Sun completes its galactic orbit. This journey takes us through regions with varying concentrations of stars that could potentially produce gamma-ray bursts. When we travel closer to stellar nurseries or areas with higher densities of massive stars, the statistical probability of encountering a GRB increases. The Sun's path through the galaxy follows a complex trajectory, periodically bringing our solar system closer to or farther from regions where star formation actively occurs. Particularly the spiral arms where massive stars are born, live their brief lives, and die spectacularly. These spiral arms represent zones of heightened risk in the cosmic landscape. Think of Earth's journey through the galaxy as a planetary road trip, where our solar system occasionally passes through cosmic storm zones with increased chances of explosive stellar events. As our sun spirals through different galactic neighborhoods over hundreds of millions of years, Earth experiences periods of varying cosmic danger. These transitional periods represent windows of increased vulnerability in Earth's long history. The cosmic forecast changes as we travel. The Milky Way itself is evolving. The galactic structure we observe today will gradually transform over billions of years through interactions with satellite galaxies, the consumption of interstellar gas, and the ongoing process of star formation and death. This changing galactic architecture directly impacts the distribution of potential GRB sources. The universe's age significantly influences gamma-ray burst frequency. GRBs were substantially more common in the early universe when star formation occurred at much higher rates and metallicity was generally lower. The first few billion years after the Big Bang represented an era of cosmic pyrotechnics, with gamma-ray bursts igniting across the cosmos at rates far exceeding what we observe today. This historical trend provides a measure of cosmic reassurance. The frequency of gamma-ray bursts has been decreasing throughout the universe's history. As the cosmos ages, the raw materials needed to form the most massive stars become increasingly locked up in long-lived stellar populations. With fewer massive stars being born, the number of potential GRB progenitors naturally declines. For Earth specifically, the statistical likelihood of experiencing another nearby gamma-ray burst diminishes with each passing billion years. The early Earth faced a considerably higher risk of cosmic radiation events than our current epoch. Yet this gradual cosmic calming offers little comfort when considering the immediate astronomical future. Within the time frame relevant to human civilization, the next 1,000 or million years, the statistical reduction in GRB frequency remains imperceptibly small. The risk endures. The critical variable in assessing potential danger is proximity. Mathematical models suggest that a gamma-ray burst would need to occur within approximately 5,000 to 8,000 light-years to pose an existential threat to Earth's biosphere, assuming the burst's energy beam was aimed directly at our solar system. This creates a danger zone around Earth. When astronomers examine this cosmic neighborhood, they find numerous massive stars that could theoretically end their lives as gamma-ray bursts. However, the orientation factor introduces a crucial limitation. The energy beams from these explosions would need to be precisely aligned with Earth to cause significant damage. This directional requirement substantially reduces the practical risk. The Milky Way's metallicity provides another mitigating factor. GRBs preferentially occur in environments with lower metal content, and our galaxy has become increasingly metal-rich over its history. Many massive stars in our cosmic vicinity lack the specific conditions needed to produce gamma-ray bursts. Combining all these variables leads to sobering, yet somewhat reassuring conclusions. The probability of Earth experiencing a dangerously aligned gamma-ray burst measures in hundreds of millions to billions of years, timeframes that far exceed recorded human history, but represent mere moments in Earth's geological chronicle. We cannot predict when or if such an event might occur. Unlike asteroid impacts, which can potentially be detected and even deflected with sufficient advance notice, gamma-ray bursts offer no early warning system. The radiation travels at light speed. We would only become aware of a burst as its energy began interacting with our atmosphere. This fundamental unpredictability represents one of the most profound cosmic realities humans must confront. A gamma-ray burst aimed at Earth represents the ultimate black swan event, rare but potentially catastrophic, arriving without warning and impossible to prevent. As our sun continues its procession around the galactic center, completing a full orbit approximately every 225 to 250 million years, we periodically approach zones with different risk profiles. This cosmic journey means Earth's exposure to potential gamma-ray bursts isn't constant, but pulses with a rhythm measured in tens of millions of years. For astrobiologists, these considerations suggest that planets near galactic centers or within unusually active star-forming regions might face gamma-ray burst frequencies incompatible with the evolution of complex biospheres. Earth's relatively quiet cosmic neighborhood may represent an important variable in explaining how life here achieved its remarkable complexity. As we continue to monitor the skies with increasingly sophisticated instruments, such as NASA's Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory, we're tracking the very forces that have shaped and might again reshape life on our planet. The discovery of GRB 221009A, the boat, demonstrates our growing capacity to witness these cosmic titans even across billions of light years. Earth's biological narrative emerges as a collaboration between terrestrial processes and celestial events. Our planet's story is inscribed by the universe itself, a humbling recognition that transforms our understanding of life's journey. In this cosmic perspective, we find both our vulnerability and our remarkable ability to witness, understand, and adapt.